Hello, Doc. Hello, classmates. I will be talking about multiple discriminant analysis, and at the same time, after the report, will be the logistic regression with a binary independent variable application. So let me start first with MDA, or the multiple discriminant analysis. For the learning objectives, after the discussion, listeners will be able to, number one, identify the major issues relating to the types of variables used and the sample size required in the application of discriminant analysis, understand the assumptions underlying discriminant analysis in assessing its appropriateness for a particular problem, describe the two computation approaches for discriminant analysis and the methods for assessing overall model fit, explain what a classification matrix is and how to develop one, and describe the ways to evaluate the predictive accuracy of the discriminant function and tell how to identify independent variables with discriminatory power, justify the use of split sample approach for validation. So first, let me first define what multiple discriminant analysis is, or what we know as MDA. Is an appropriate technique when the dependent variable is categorical, nominal, or non-metric, and the independent variables are metric. The single dependent variable can have two, three, or more categories. That is why it's important that we can apply this one to SPSS, because if we're going to treat the independent variables, they are being considered as metric variables. So just for example, talking about gender, we do have male versus female. We have heavy users versus light users, user purchasers and non-purchasers, good credit risks versus poor credit risk, members versus non-members. So here, as you can see, this is a very good example as to how KitchenAid survey result for the evaluation of the new consumer product. Basically, the evaluation is made on the 0, which is considered as very poor, and 10, which is considered excellent in terms of rating. The two groups are being classified, as you can see here in the graph, in the table, what I mean is group 1, who says that they would somehow purchase. And the 1 to 5 are the subject numbers. Contrary to that are group 2, which says they would not purchase, which is 6 to 10 of the subject number. Now, we do have three different variables that we consider in terms of durability, performance, and style. And basically, the consumers or the purchase intention of the consumers are being rated accordingly. In this particular table, we also got the group mean, which is the group mean of every variable, durability, performance, and style. And at the same time, knowing the difference between the group means. Later on, I will be explaining to you as to how we can run in SPSS in terms of having multiple discriminant analysis. Now, for this one, this is just a very simple way of doing so, knowing exactly how we can interpret certain survey results for having certain evaluation as we come up with parameters in terms of rating. So here, this is an illustration of two-group discriminant analysis. As you can see in this one, consumer A and consumer B are both actually in the same proportionate angle, which projects in the same direction, and looking into the symmetrical way of discriminant function, which goes beyond the z level, which is below x1. And here, discriminant analysis decision processes, and we have different stages of doing that. First is we need to identify objectives of discriminant analysis. Second stage is the research design for discriminant analysis. Third, assumption of discriminant analysis. Fourth is estimation of discriminant model and assessing overall fit. Fifth, interpretation of the results. And sixth would be validation of the results. So let's take a look at one by one for each particular stage. So first, we have stage 1, which is an objective of discriminant analysis. So for this stage, it's more likely in determining if statistically significant differences exists between the two or more priori defined groups. And at the same time, in this particular stage, we happen to know that we can somehow identify the relative importance of each of the independent variables in predicting group members. We can somehow see the strengths of it. Third is we establish the number of composition of the dimensions of discrimination between groups formed from the set of independent variables. That is when there are more than two groups. So you should examine and somehow name each significant discriminant function, the number of significant functions, which determines, in terms of dimension, discriminant function, that what they represent in distinguishing the groups. And of course, we need to develop procedures for classifying objects. So basically, individual firms or products, whatever is the type of variable that we're using, which are being grouped into, and then examining the predictive accuracy, which we need to hit certain ratio of discriminant function to see if it's acceptable, which is greater than 25% increase. Now, looking into stage two, it has something to do with the research design for discriminant analysis. And for this one, it has something to do with the selection of the dependent and independent variables. And perhaps we can somehow determine the sample size, which is the total and per variable. So the sample size should be immense, meaning to say that it wouldn't work if we have a low sample size. And somehow we need to consider equal sample size as well, and also sample divisions for validation purposes. Now, we also have to consider converting metric variables into non-metric ones. So, most common approach is that we tend to use the metric scale response to develop non-metric categories. So, say for example, to cite an example, we use a question asking the typical number of soft drinks consumed per day and develop a three-way category variable of 0 drinks for non-user, 1 to 5 for light users, and 5 and beyond for heavy users as our parametric scale. And somehow, contrary to that, is the polar extremes approach. This means to say that there's comparison and somehow compares only extreme two groups and exclude the middle group. So we also have to consider some rules of thumb in here. For discriminant analysis design, for a dependent variable, it must be non-metric, representing groups of objects that are expected to differ on the independent variables. So we have to choose carefully which is the independent and dependent variable. So when we talk about choosing dependent variable, that would mean that it somehow best represents the group differences of interest. Another key idea that we have to consider is we need to define groups that are substantially different and at the same time minimizes the number of categories while still meeting the research objective. So with that, in converting metric variables to non-metric scale for use as dependent variable, we always consider using extreme groups that we have to maximize the group differences. At the same time, for independent variables, it must identify differences between at least two groups to be any use in discriminant analysis. That is why this falls into multivariate analysis. Just to continue with the rule of thumb, the sample size must be large enough, as I mentioned earlier. We have at least one more observation per group than the number of independent variables, but striving for at least 20 cases per group. The 20 cases per independent variable with a minimum recommended level of 5 observations per variable, and have at least one observation per group than the number of independent variable, but striving for at least 20 cases per group. So have a large enough sample to divide into estimation, and we can somehow hold out sample and each meeting that above requirements, no? Now, we also need to consider how we're going to have it assess the equality of covariance matrices with the boxes M test. I will be running that in SPSS, but you have to apply a conservative significance level of 0.01, examining the independent variables for univariate normality, and at the same time, multi-collinearity in terms of the independent variables, which markedly reduce the estimated impact of the independent variables in the derived discriminant function, particularly in the stepwise estimation process which is being used. Now, we also have key assumptions. Now, this is stage three that we have to assume of discriminant analysis. So, for multivariate normality of the independent variables needs to be assumed. And at the same time, equal variance and covariance for the group is also being assumed. And other assumptions that we also have to consider: minimal multicollinearity among independent variables, and group sample sizes relatively equal to one another, linear relationship, and also elimination of outliers. And stage four, we need to have estimation of the discriminant model and assessing overall fit. Now, for this one, we need to select an estimation model, and it somehow fits into your own topic. It's very important that we also have simultaneous estimation. All independent variables are considered concurrently. And stepwise estimation process would somehow include the independent variables which are entered into discriminant function one at a time. And also, when estimating the discriminant function, it's very important as well that the stepwise procedures begins with the independent variables, not in the model itself. So we really have to identify first independent variables in order for us to select for inclusions, which we somehow base it into two different ways. Statistically significant difference across group, which has zero point zero 0.05 or less required for entry, and of course the largest Mahalobi's distance, which is d squared between the group. And we also need to have assessment for the overall fit, for the overall model fit. So calculating the discrimination z, which somehow scores for every observation. That's very important as well. And we also have to take note of evaluating group differences in the discriminant z scores and assessing group membership prediction accuracy. And now we are going to have the assessment group membership prediction accuracy. So what are the major considerations that we have to bear in mind as researcher? It is very important that the statistical and practical rationale for developing classification matrices should be noted. And also cutting scores determination. We need to construct of the classification matrices and standards for assessing classification accuracy. Now, a model estimation and model fit has some rules of thumb that we have to consider. So model estimation and model fit, although stepwise estimation seems optimal by selecting the most parsimonies of maximally discriminating variables, we have to be aware of it, no, in terms of its impact of multicollinearity on the assessment of each variable's discriminatory power. And of course, the overall model should somehow assess the statistical significance between groups of the discriminant z scores, but doesn't really assess predictive accuracy. And with more than two groups, do not confine your analysis if there are two to only the statistical significant discriminant function, but we also have to consider if non-significant function with significant level of up to 3 could somehow add exploratory power. So calculating the optimum cutting score. So we also have issues that we have to consider. Okay, so it is also important that we have to define the prior probabilities based either on the relative sample size of the observed group or specified by the researcher. Either we do assume to have it equally done or with values set by the researcher. And of course, we have to calculate the optimum cutting scores value as weighted average based on the assumed sizes of the group, which is being derived with a sample size which we are going to run in our SPSS. So here in this slide, you're going to see the optimal cutting score with equal sample sizes. For this one, you can see that the sample sizes are somehow equal. That means to say if it has an equal sample, it can lead to equal variances between samples, which we happen to know that it would not affect the assumption in tests like MANOVA if it's multiple already. And of course, having equal sample sizes and variances don't somehow affect statistical power and even type 1 error rates. Now here, as you can see, it is not somehow equally distributed in terms of the grouping. So group A is smaller than group B. This is a very good example of optimal cutting scores with an equal sample size. And this was being cited by one of my references, according to Rusticus of 2014, that if you can see that there is no an unequal sample size here, which somehow lead to unequal variances between the samples, and which would somehow affect assumption of equal variances of our test like the ANOVA or even ANOVA. Having both unequal sample sizes and variances would somehow dramatically affect statistical power and type 1 error. Okay. And then we had to establish standards of comparison for the hit ratios. So group sizes determine standards based on equal group sizes and unequal group sizes, which is two different criteria that we need to consider. First is the maximum chance of criterion, and the other one is proportional chance of criterion, which was shown in our previous illustration. So here we also have classification of matrix of the new product consumers. No? So here, this is a predicted group which is being divided into two, as you've noticed. No, as we have seen that one in the previous report. The ones who would purchase has predicted to have 22, and those who would not purchase are being predicted to have it 20. No? So basically, with the actual total, it's around 25, with a percent correct classification of 88% for group 1 and 80% of group 2. So that means to say that percently correct classified hit ratio, as to how it is being computed, would be 100 times 22 plus 20 divided by 40. So we have to get first 22 plus 20 divided by 50 before we're going to use it as a multiplicand of 100 to get an 84%. So assessing predictive accuracy, which is a rule of thumb, okay? Another thing that we have to consider is the classification metric would somehow hit ratio, which replaces R as the measure of model fit. So first things first is to assess the hit ratio, both overall and by group. And if the estimation and analysis samples both exceeded 100 cases of each group, which somehow exceeds 20 cases, derive separate standard for each sample. If not, then derive a single standard from the overall sample. It's also very important to analyze the misclassified observation both graphically as we will go along and show you a territorial map and empirically the Mahalanobis D2. Assessing predictive accuracy, which is a rule of thumb, still a continuation. Assessing predictive accuracy, there are multiple criteria for comparison to hit ratio, and the maximum chance of criterion for evaluating the hit ratio is the most conservative, giving the highest baseline value to exceed. And be cautious in using maximum chance criterion in situations with overall samples, which is less than 10, or group sizes under 20. And it's very important that there is a proportional chance of criterion considering all groups in establishing the comparison standards and is the most popular. And of course, we have to consider the actual predictive accuracy to hit the ratio and should exceed the any criterion value at least 25%. Stage 5 is something to do with the interpretation of the results. And we have three different methods to do that, particularly the standardized discriminant weights, discriminant loading, which includes the structure correlation, and lastly, the partial F values. So interpretation of the results. So there are two or more functions that we have considered, that we need to consider. First is the rotation of discriminant function and then the potency index. Later, I will be showing you how important to compute the potency index because this would somehow determine the discriminant value after we've come up with the final result of it, of the computation. So graphical display of discriminant scores and loading. We have territorial map, as what I've mentioned, most common method, and we also have the vector plot of discriminant loadings, preferably the rotated loadings, and it's actually the simplest approach. So plotting procedures for vectors. First, there are three steps. First is selecting the variables. Next is you have to stretch the vectors and plotting the group of centroids. So this is a very good example of a territorial map for the three-group discriminant analysis. So here we have x1 and x2, as you can see, and it's being divided into function 1 and function 2. We do have legends to consider the group centroids over 5 years, 1 to 5 years, and less than 1 year, as what we cited with our previous example. And as you can see, it is being scattered. Usually it's being trajected towards the upper part or in the positive way. And we can also see here that they are more clustered okay, within 1 to 5 years, as you can see in that particular graph. And for territorial mapping, we also have to consider that territorial map would somehow help us to study the relationship between the groups and the discriminant functions. And somehow combined with the structure matrix, would somehow have a great result. And it gives us a graphical interpretation of the relationship between predictors and even the group that we are trying to study. Then interpreting and validating discriminant function, which is rule of thumb. So interpreting and validating discriminant functions, it's very important. We also have the discriminant loadings are the preferred method to assess the contribution of each variable to a discriminant function because first, they are standardized measure of importance, which range from 0 to 1. The available for all independent variables, whether used in the estimation process or not, and also the unaffected by multicollinearity. And loading exceeded plus minus 0.40 are considered substantive for interpretation purposes of the study. Continuation, interpreting and validating discriminant function. If there is more than one discriminant function, we have to bear in mind that we need to use rotated loadings and also we need to assess each variable's contribution across all the functions with a potency index. And of course, discriminant function must be validated either the handout sample or one of the leave one out procedure. Stage 6 is something to do with utilization of holdout sample and cross-validation. All right, so in terms of application SPSS, no, I am trying to do screenshots because if I'm going to do it live, it would somehow lag my internet connection and I might lose my connection in terms of its bandwidth no that it's using if I'll open it. It could somehow really lag my computer. It's because I think no I the file is really heavy. So as you can see, this a very good example of a data which has been extracted in a Microsoft Excel, no? After I was able to tally it out, no? So for this particular presentation, you can see there that there are abbreviations already I'm using. So when you talk about BP, it has something to do with banking products. SB is something to do with staff behavior. BI is bank's interest. E-bank is for EB, and PS is for physical surroundings. And PUPVFB is public bank, private bank, and foreign bank. So I'm trying to use here a very good example in terms of banking and finance. So how are you going to run that one in SPSS? So you just go to Analyze. You just have to open your SPSS, then press Analyze, press Classify, and then Discriminant. And once you're done, it will show you this one. No? So among those BPSB, those abbreviation BI, EB, and PS, for the grouping variable, you need to put here PUPVFB, which is considered to be in the upper portion. Okay, that would be your dependent variable, and you need to consider as well the discriminant analysis, defining the range of a minimum of 1 to a maximum of 3. And then you just have to press continue. Next is the independence. So the independence would somehow include banking products, staff behavior, bank's interest, e-banks, and physical surrounding, which should be clustered in this part. You just have to check enter independence together. Click here statistics, and you have to click means, univariate ANOVAs, boxes M, Fishers, and unstandardized. And then you hit continue. And after which everything has been done, then you press OK. So this is the result of the data which is being treated, okay? So here, when we talk about group statistics, no, as you can see, there are values, okay? 1 represents public, 2 represents private, and 3 represents foreign bank. And as you can see here, interpreting the mean value of the public, private, and foreign bank, which has something to do with the group statistics, no? It's just that the mean and also the standard deviation. And let's also concentrate as well with the banking product variable. Looking at into the customers are satisfied with number 1, no? As you can see here in this part, in number 1 for the public, no? Customers are really satisfied with number 1 in public banks since the mean is less than that of a private and foreign bank, okay? So you can see here with the mean that mostly in the public banks, no, it's kind of lower. Next is the test of equality of group means. So in this test, we are going to identify here the F value and significant value. Significant value, this part, in this last column, which is also being considered as the p value, its significance if it's somehow less than 0.05. So I think we do have significant results here, no? SB, EB, and PS, no? And of course, we also see here the Wilks lambda. No, so what does that mean? When you talk about Wilks lambda, it has something to do with a particular test, no, of a multivariate test, which somehow has a significance in terms of variates between 0 and 1, and somehow value closest to 1 indicates the difference that is not significant at all. Okay. Now you can see here, I'm sorry for it's so blurred because this one is really small and I'm just maximizing it. For the result, the boxes M here would somehow be considered as the test of homogeneity, no, of the covariance matrices. Okay, it tests null hypothesis of equal population covariance matrices. And then here is a summary of canonical discriminant factors, which is your eigenvalue. This is a very important value that we are going to use during our computation. You know that we're going to do it in the Excel file because whatever is being run in the SPSS, you need to extract the values and you need to compute it manually um, with the use of Microsoft Excel. Okay. So for the summary of canonical discriminant function, this is something to do with, it can be done to find the potency value and of course the potency index. No? Those are very important things that we are considering. And the structure matrix, as you can see, no? Structure matrix will somehow show correlation of each variable with each discriminant function. And others call it discriminant needed for potency value and potency index. Okay? So here, as you can see, this is already the Microsoft, no? Sorry, the Excel form. Sorry, I keep on saying Microsoft, but it's Excel that we are using in terms of computing it. So as you can see here in the structure matrix, in the bottom part, the right bottom corner, no, it says structure matrix, which is the function 1 and function 2. We are able to extract this one in the SPSS, no? So the staff behavior, the e-banking services, the banking product, the bank's interest, and physical surrounding. And there is a particular result that we are considering for function 1 and function 2. Now here, there are two different groups that we are comparing. We have here discriminant loading number 1 and also the discriminant loading number 2. Okay, so let's start first in the upper left corner. As you can see, the variables are being placed. There are 5 variables. Discriminant loading, that those are the value that is being extracted in the structure matrix. Have you noticed that? It's 0.752, 0.545, 0.494, negative 0.158, and 0.481. Now, we need to create the third column, which we need to squared, right? The squared, we need to square the loadings. So what is the formula for that? So you just have to get the squared, no? Or the, you just have to square the discriminant loading. So 0.752, and then you try to square that one, no? Usually when you're going to type that one in Microsoft Excel, the one which has, you're just going to click B2, okay? And then B2, then um, usually in the keyboard, it's in number 6, no? In the up, if you're going to shift and press number 6 in your keyboard, you can see there that an arrow pointing up, no? Somehow it is known to be squared, no? So once you press that, you just have to put 2 and then you will be able to get the square loading, which is 0.56, so on and so forth, no? And in doing so, you just have to click the 0.565504, then drag it down for you to get those values as you can see in the screen. Now, we're going to consider the relative eigenvalue. So how did we come up with 0.7 eigenvalue? So in the bottom part, you can see there at the bottom left corner, no, it says their eigenvalue. So for the function, the eigenvalue for function number 1 is 0.049 and function number 2 is 0.021. Where did we get that kind of value? That's what we've run in SPSS. Remember that it is just a summary right now that we are doing, and we are able to extract those data which is being treated in our SPSS. And then we're going to get now the relative eigenvalue. How are you going to come up with a particular result of 0.7? It's just very simple. For function number 1, the value of eigenvalue for function number 1 is 0.049. You just have to divide it with the sum of 0.049 and function 2, which represents 0.021. So the result with that, you have to divide it with 0.049 for function 1. That's why you come up with 0.7 for the result. Now, another example is function number 2. So identify the result of function number 2, which is 0. Sorry, it should be 0.021. It's not 0.21, but it's 0.021 divided by the sum, no, of 0.021 plus 0.021 to come up with 0.3. 0.3 is being used as a relative eigenvalue to our discriminant loading number 2 for the potency index for value number 2. Okay? And now, once we've got no the relative eigenvalue, no, um, here in the upper left corner, you just have to multiply the squared surrounding with the relative eigenvalue. So C times D is the formula for that. No? So C2 times D2. And then you come up with a potency value of 0.395. And then you just have to click that and drag it at the bottom for you to come up with those results of the other one. Same thing as what we'll be doing for the value number 2 or potency value number 2 to get that kind of value. Then, how are we going to do that again? Discriminant loading of all the variables, okay? That, where did you get 0.402, 0.271, negative 0.006, 0.83, and 0.61? You got that here in function number 2 in the structure matrix, okay? So you get the function number 2, then you're going to do the squared loading. Then again, the formula for that is B2 squared the number 2. Okay? So that's the kuan. That is the result. 0.16, 0.07, 0.00036, 0.69, 0.38. And also, the relative eigenvalue for function number 2 is 0.3 as how we're going to compute it. No? And then drag it down for it to have a copy paste lang, and then potency value 2 has something to do with um, the result of the multiplication, no, of 0.16 and 0.3. Okay? So the result for that is so on and so forth for potency value 2 column. Now, once you got potency value number 1 and potency value number 2, we're going to get the potency index. If we're going to get the potency index, we just have to add potency value 1 and potency value 2. So the formula for that is A, B, C, D, E, E1 plus J. Okay? E1 plus J1. And that would be the total for the potency index. And then again, potency index is equivalent to potency value 1 and potency value 2. Okay? And that is the result, and you just have to drag that. And after which, it's very obvious, no, to see whichever is the highest, which is just near the nearest one, no. So we're going to rank it, no. So 0.44 ranks number 1, followed by 0.2766, 0.2256, no, 0.2299, and then 0.2256, and last is 0.17. No? So here in the potency index, we can say that staff behavior can be a discriminant, no, can be a very good discriminant value in terms of how it affects into the study. So that's how we're going to interpret it with our research study.